Welcome to another exciting video on our channel. Today, we're diving deep into the world of theoretical physics and exploring string theory, one of the most intriguing and mind-boggling theories that try to explain the nature of reality. For decades, physicists have been puzzled by the apparent inconsistency between two fundamental theories of nature, quantum mechanics and general relativity. String theory proposes a revolutionary idea that there is an underlying structure of the universe at the smallest scales that can explain the laws of physics. According to string theory, the building blocks of everything in the universe are not particles, but tiny one-dimensional strings vibrating at different frequencies. These strings can interact and combine to produce all the particles and force fields we observe in the world around us. String theory suggests that there are 10 dimensions, with the additional 6 dimensions hidden from our everyday experience and only accessible at the smallest scales. These extra dimensions are curled up tightly, forming a tiny space known as Calabi-Yau manifolds. The shape of these manifolds determines the masses, charges, and other properties of particles in the universe. One of the biggest challenges for physicists has been to reconcile the weird and counterintuitive world of quantum mechanics with the classical world of general relativity. String theory proposes that the universe is governed by a single set of laws, with quantum mechanics and general relativity emerging as different limits of the same theory. This idea is known as the holographic principle, which suggests that all the information contained within a region of space is encoded on its boundary. So, are there any experimental tests or evidence supporting string theory? Unfortunately, string theory is a highly speculative theory that currently lacks experimental evidence. Some physicists argue that it is not even a scientific theory in the traditional sense, as it cannot be tested or falsified easily. However, there are some indirect hints that suggest string theory might be on the right track. For instance, string theory predicts the existence of particles that are too heavy to be detected by current experiments, such as supersymmetric particles and extra dimensions. String theory not only provides a new way of thinking about the nature of reality, but also has profound implications for other fields of physics and cosmology. It proposes that there are many possible universes, each with different physical laws and constants. This idea forms the basis of the multiverse hypothesis, which is one of the most controversial and debated concepts in modern physics. Now, you might be wondering if there are alternative theories or competing ideas to string theory. Yes, there are several alternative theories and competing ideas to string theory. Some of them, such as loop quantum gravity and causal dynamical triangulation, try to resolve the same issues as string theory, but using a different mathematical formalism. Others, such as brane-world scenarios, propose a different structure of the universe with extra dimensions accessible to gravity. Now, let's explore, how does string theory relate to other branches of theoretical physics, such as particle physics and cosmology? String theory is highly interdisciplinary and has connections to various fields of theoretical physics. It is closely related to particle physics, as it proposes a new way of understanding the fundamental building blocks of the universe. It also has implications for cosmology, where it might provide a way of understanding the origin and evolution of the universe. String theory is a complex and challenging area of research with many fundamental questions yet to be answered. Some of the most pressing questions include the validity of the theory itself, the role of extra dimensions, and the possible string theory has a long and complex history. The first version of string theory was proposed in the early 1960s. However, it was not until the 1980s that string theory began to be taken seriously by physicists. In the 1990s, there was a major breakthrough in string theory, known as the second superstring revolution. This breakthrough led to a unification of the 5 different versions of string theory into a single theory known as M theory. There are 2 main approaches to string theory: the perturbative approach and the non-perturbative approach. The perturbative approach is based on the idea that string theory can be treated as a perturbation of a simpler theory. There have been a number of important developments in string theory in recent years. One of the most important developments is the discovery of new mathematical structures, known as Calabi-Yau manifolds, which can be used to describe the extra dimensions of string theory. Another important development is the development of new computer simulations that can be used to study string theory. And that concludes our exploration of string theory, one of the most fascinating subjects in theoretical physics. We've covered its foundations, its implications for our understanding of the universe, and the challenges researchers face in unraveling its mysteries. Remember, science is an ever-evolving field, and new discoveries are waiting just around the corner. If you found this video intriguing, don't forget to like and subscribe to our channel for more mind-expanding scientific content. Feel free to leave your comments and questions below, and we'll be sure to address them in future videos. Until next time, keep exploring the wonders of the universe.